Okay, let's start. Welcome to this week's colloquium.
All right, it's a great pleasure to introduce Dr. Charles Steinhardt from the Department of Physics and Astronomy from Mizzou, University of Missouri in Columbia. Let me say a few words about his academic career. He got a PhD at Harvard University in 2010, and then he moved to Kaburi IBMU in Japan, which is where he actually had a bit of overlap. And then his next postdoc at Caltech. And then he joined the Galaxies Center in Nielsborg Institute in Copenhagen, Denmark, as assistant professor in 2016. And then he got promoted to associate professor there in 2019. But then he decided to move to Mizzou in 2024. So he has a broad interest, including cosmology and galaxy evolution, and then he's going to tell us one of the open topics in the galaxy formation today. So,
thank you. So yeah, I just moved here, so I haven't been to Rolla before. I actually had known about Rolla when I was a kid. There was this math competition in high school that was a national thing that a couple of people, one at Rolla and one at, I think, Rose-Hulman, kind of put together. So I had known about the reputation, but this is my first chance to actually visit. So yeah, thank you for having me. I work on a number of different things. So some in cosmology, some in machine learning. But what I'm going to do here is I'm going to tell you about some of the exciting things we're discovering in galaxy evolution. So I think fundamentally, the thing that makes galaxy evolution most difficult observationally is this big mismatch between what you observe and where most of the mass is. That basically you're only seeing this tiny fraction of the mass, or hold on, is that going to work? Yes, it's going to work. Okay. Or we also kind of think of as the tip of the iceberg. Now, I really shouldn't come to a physics department and show it this way. So it is actually the case, if you go online and you just kind of look for like pictures of tip of the iceberg, this is what you see. But it's been pointed out to me that actually icebergs don't do this. And there's a wonderful site you can play with called Iceberger, where you can actually, solve the Navier-Stokes equation and so forth. And so apparently this is actually the way we should think about icebergs. But since this is the one you find online, we'll kind of go with it. So the point is that the mass that you see is only coming, the light that you see is coming from only a very tiny fraction of the mass. So first off, most of the mass in one of these galaxies is dark matter. We don't know what the dark matter is, but as the name implies, it has mass and it's not giving off light, so we don't see it. Okay. Then of the ordinary matter of the baryons, again, most of those baryons don't end up in stars, which means they're again effectively invisible to us. And then finally, even of the ones that do become stars, the light that we see is dominated only by these rare, very high mass stars. And all of the low mass stars, which contain most of the mass, essentially still end up invisible. And when you put all of these things together, depending on the galaxy we look at, the light that we see is typically coming from anywhere between maybe a part in 1,000 and a part in 1,000,000 of the mass. All of the rest is basically invisible. So it's kind of even worse than the iceberg in terms of the fraction that we see. And if we want to understand how galaxies work, we have to basically reason our way from the small fraction of light that we see, of mass that we see, to everything which is invisible. Okay, how do we do this? Well, imagine that you're in an ocean and what you see is tips of icebergs all over the horizon. And there's only one iceberg that you're on and you can get a really good look at. Okay, well, what you do is you basically assume that all icebergs are identical and they're all made of ice and they all look exactly like the iceberg that you're on. And you might even have a good reason to believe that this can't be true. But you're kind of stuck, right? For lack of any more information, we end up kind of assuming that all icebergs are made of ice, basically. And so the same is true with the way that we've been looking at distant galaxies. We take the handful of nearby galaxies that we can get really good information about, and we use that to scale from the small fraction of mass that we can see to everything else that we can't. And so where I started getting interested in the problem was realizing that actually this is starting to break down. So one of the ways that we can think about this is we can think about the initial formation process for how galaxies assemble. So if we think about how the story of a galaxy, the first step is that gravity assembles the ingredients. And this is even something that we can start to measure. So we can look at something like the cosmic microwave background, this relic, from relatively shortly after the Big Bang, where we're seeing these hot spots with a little bit extra material and these cold spots where there's a little less material than average, that eventually are going to become the building blocks where gravity assembles them into galaxies. This, by the way, is also one where you'll often see a picture like this, in sort of media or something like that. It's worth pointing out that this is really exaggerating the differences. So the difference between the hot and cold spots here is something like a part per thousand. And that's another interesting story, how it comes to be so similar. But on some level, really, you should be thinking about this as kind of almost constant, right? And you're seeing these very tiny differences that are being exaggerated kind of to show you the formation of structure. So what happens is that gravity takes these hot spots, and there's a little bit extra gravity, so material kind of comes together and assembles. And you can basically write a simulation and start to kind of see the assembly of structure. And we can even freeze one of these simulations and just kind of count all of the places that galaxies are starting to assemble. And we can compare that with what we actually observe and kind of see how these two things compare. Okay. So where I first started getting interested in the problem was looking at this comparison. So what I'm showing you here, basically in each of these panels, what you're seeing is the green. So the green is basically from the simulations. What would the distribution of galaxies look like if you efficiently take all of the ingredients that are there and assemble them into stars? Okay. And the magenta is what we actually observe. So if we start at the top left, this is sort of the most local answer. What we see is there's kind of this little knee in the curve where it seems like all of the available ingredients have been turned into stars. And then on either end, there's something a little bit missing. So there are different kinds of feedback processes that stop you from fully using all of the ingredients and making stars out of them. Okay, and this is all fine. But if we start to think about what this should look like in the early universe, our understanding of these feedback processes was that they take some time for the feedback to really take hold. And so what we thought would happen is that as you go toward early times, sort of toward the bottom right, the magenta and the green curve should look more and more similar because the feedback hasn't really turned on yet, and we can use all of the ingredients. And to a large extent, that's what you see. They are looking more and more similar. But there's a little bit of a problem, which is if you look at the high mass end, the magenta curve starts to approach the green. And somewhere here around a redshift of 4, so like 1.5 billion or something years after the Big Bang, they're the same. And then the magenta moves past the green. And that's a big problem, because that means that you've actually assembled more stars than you have the ingredients for. And so if this is really true, something fundamentally is broken in our understanding of how galaxies assemble. And if you start to look at this toward earlier and earlier times, what we see is the higher redshift you go, the earlier time you go, the more the points. That's the equivalent of the magenta curve, the galaxies we see, the more they lie above these lines, which is the equivalent of the green curve, kind of what you're able to assemble. And so if this is true, it's telling you something really exciting. It's basically saying that we thought we understood how galaxies assemble their ingredients just under gravity alone from these initial fluctuations. But we're wrong. They assemble ingredients earlier than under gravity alone. We're missing some force. There's some additional attractive force that brings things together. And we're about to learn maybe something exciting about properties of dark matter or something like that, but some new fundamental physics would be needed. But as exciting as it would be to reach that conclusion, we kind of have to pause a little bit, because I have to point out that these points are not what we observe. These points are the entire iceberg. We only observe the little tip of the iceberg. So before jumping to the conclusion that we need some kind of novel physics, we better ask whether instead maybe we're just seeing that this iceberg approximation breaks down, right? Maybe the first galaxies really are not identical to local analogs. So the consensus, when I kind of first put this result out, wow, almost a decade ago, the consensus was basically that maybe what was wrong was this stellar baryon fraction. That locally, maybe 10% of the baryons end up in stars, but maybe what's happening is the first baryons to fall into a galaxy are very efficient at making stars because there's not time for feedback yet. So maybe you could have, 10 times as many stars as we thought we could have, right? So that was the idea until about 3 years ago. Because when James Webb first launched, we could push this. Remember, it was getting worse the earlier we went. We could push this to even higher redshifts, to even earlier times. And the first results from James Webb now said that there was even more stellar mass, even more stars than all of the available baryons. And so this is no longer a solution. Okay, so we're back to having something broken. But again, before you really want to decide you need exotic physics, there are a couple of other assumptions in here as well that are important. And so the one that I'm going to focus on for the rest of the talk is this one at the top, thinking about the ratio of high mass to low mass stars. First, the physics that kind of controls that and whether it should be different in the early universe, and then some of the things that we can learn as a result. So one other thing maybe that I should show you before we talk about the answer is what it really means to have this iceberg approximation and why it's so important. Okay, so I can't give an astronomy talk without showing some kind of pretty picture of a galaxy. Okay, but the truth is that the distant galaxies that we work with really don't look like this. We don't have anything close to that resolution. Ours look kind of like this. Okay, if we're really lucky, maybe we have enough observing time that we can get a spectrum. We can look at the flux as a function of wavelength and we get something like this. But even this is difficult because for the earliest galaxies, getting something like this will often take anywhere from maybe 1 to 100 hours per galaxy. And so if you now want to have big catalogs of thousands of galaxies, you can quickly see that this is not going to be possible. You can get spectra for a few examples, but an enormous spectroscopic catalog for faint objects is still beyond our capabilities. Okay, but fortunately, it turns out we can take a shortcut, which is that many of the features of galaxies really don't change that much from one galaxy to another. So for example, if I want to identify the highest redshift galaxies, well, often the easiest way to do this is from features in the spectrum, like this big break here, okay, where on the left side, there's a lot less flux than on the right. And this is basically because most of these galaxies are made of hydrogen. So if we think about a hydrogen atom trying to absorb photons, there's some range in which it can only absorb photons on a specific wavelength that take the electron from one energy level to another. But if I hit it with a high enough energy photon, it can always absorb that photon and become ionized. And so what's happening is this break is really driven by sort of excited electrons in the n=2 state, but the same will be true for the ground state. And so if I take shorter wavelengths than that, hydrogen can always absorb the photon. It removes most of the emission that you see. So if I take a bunch of distant galaxies and zoom way out, you can actually pick out the redshift without seeing the details of the spectrum. All you have to do is find this break, and depending upon the wavelength of the break, you can get the redshift. So maybe if I want to find these distant galaxies, maybe I don't need to spend 1 to 100 hours per galaxy and get a spectrum for everything. Maybe what I can do instead is I can just observe the galaxy in a handful of different broad filters. If I make a filter, say, 100 times broader, then I'm getting photons at 100 times the rate. So it's much quicker to kind of take these observations. And if I want to identify the high redshift galaxies, I just look for something where I see flux in these 2 bands on the right, and I don't see any flux on the left. And that's what you're seeing here. Okay. These letters are just because astronomers, I guess, didn't learn the alphabet when we were labeling bands or something, but they kind of correspond to the colors that you saw. I'll blow it up a little bit, and you can see. The reason we can see this is a high redshift galaxy is because we see a bunch of light in these redder bands, but not the bluer ones. Okay. So the good news is that this lets us efficiently find these very high redshift distant galaxies. But it also means this is all of the information we have about them, and we still need to learn their properties. So the way that we actually take this iceberg approximation and apply it is we take the physics that we learned from very local galaxies, and we use it to build a whole series of models, where each of these models is generated from different, potential physical parameters. And actually, it's worse than this. This is kind of one parameter, and it's a whole series of different parameters that come together. But the idea is, you take this big library of possible templates, and you simply ask which one fits best. And whichever one fits best, you basically assume that the properties that produce that template are your best guess for the properties of that galaxy. And you can still fit from a library of templates with potentially only a few different points, which is what we get from these broad bands. So this is how we've been taking these large galaxy surveys and these otherwise difficult observations of things and turning them into properties. Okay. So one of the assumptions that's made then as part of this iceberg approach comes down to that. Remember I showed you that one of the assumptions is something about the ratio of high mass to low mass stars. So the way this is typically described is in terms of what we call the initial mass function. Basically, when you make a bunch of stars, what is the mass distribution that you get? And this initial mass function, or IMF, this is already one of the difficult observational problems historically in understanding our own galaxy. So that over the past century, we've had a bunch of different ideas for exactly what this mass distribution might look like. And it's not even sometimes when I show you something like this, it would just be the case, well, maybe one of these was the old answer and then we, got a newer answer. It's actually the case that if you look at current models that are being used, different groups actually will pick different initial mass functions. So this is still something where actively there's debate over which one of these is the best description of the mass distribution in a galaxy. Okay. But it makes an enormous difference because if you use different IMFs, you're almost reporting your results in different units. You agree on what the luminosity is, but you disagree on what the invisible part is. Still, though, what all of these groups are doing is they're taking their favorite version of what it looks like in the Milky Way, and they're assuming that it's universal. Okay. But if we think about the physics of star formation, it's actually not that simple. So the physics of star formation is really a competition at its core between gravity, which wants to just take clouds and bring them together, and thermodynamics, which instead wants the cloud to expand. So to begin with, the conditions that cause stars to form, the condition is basically that gravity wins that battle. But then typically these large molecular clouds might be 10 to the 4 times the mass of the sun or something like that. As they start to collapse, we get additional thermal fluctuations. And so there's an additional competition between gravity and thermodynamics where it determines whether the cloud's going to fragment into smaller pieces and make a bunch of small stars, or whether it's not going to fragment and tend to keep bigger stars. And so if we change the temperature in a star-forming cloud, we should expect to get a different initial mass function. So here's some idea of what that looks like. The yellow would be an example of the Milky Way-like initial mass function. If we increase the temperature for something like the blue, what happens is at higher temperature, it's easier to wipe out small fluctuations. So you make a lot fewer low-mass stars. And similarly, if we were to have clouds that are cooler than the Milky Way, like the red here, the opposite would happen. We would tend to have more of the low-mass stars. So we might call the red one a bottom-heavy initial mass function, and the blue one a bottom-light initial mass function. Okay. But the point is that if you change temperatures in star-forming regions, then this distribution should be sensitive to it. And so the assumption that the IMF that we measure in the Milky Way is universal is basically an assumption that at all times, under all conditions in all galaxies, you have exactly the same conditions in these molecular clouds that collapse. And we kind of know that that's not true. So for example, in the Milky Way, this is happening at about 20 Kelvin today, okay? However, we now see galaxies very early in the universe. We see galaxies above a redshift of 10. At a redshift of 10, the cosmic microwave background temperature isn't 3 Kelvin, it's 30 Kelvin. And so you're basically in this thermal bath at 30 Kelvin. And there are surely other processes that also heat the clouds. So it's probably warmer than 30 Kelvin. But it's definitely not 20 Kelvin. And so something's changing. There have to be fewer low mass stars at high redshift than you would assume if you have a Milky Way initial mass function. Okay. Now, what I'd really like to be able to do is just say, oh, well, this is simple. Let's just measure the gas temperatures and we can figure out which IMF to use. But observationally, measuring gas temperatures is a nearly impossible thing to do, partly for technical reasons, and partly because if you have a set of clouds at different temperatures, the luminosity, so black body radiation, right, goes as T to the 4th. So basically, the luminosity, if you have both hot and cold clouds, is dominated by the hot cloud. But the star formation, well, that's where gravity wins as easily as possible. That's dominated by the cold cloud. And so even if you can measure gas temperatures, you're often measuring the wrong gas temperatures. So it's difficult to connect the two. Okay. What I can do is I can show you dust temperatures. And there are a lot of reasons that dust is not gas, and these have their own difficulties. But we still might guess that they have related kinds of physics and related kinds of feedback. And the main takeaway from dust temperatures is just that this is complicated. Okay, these are not constant. There's a dependence, higher star formation rate makes the temperature go up. Higher mass, okay, that makes the temperature go down. Change the redshift from one redshift to another. There's also some evolution. Things are becoming a little hotter toward high redshift. So this is complicated. This is not one size fits all. This is telling you that there's actually a complex set of feedback in galaxies where the dust temperature is related to other things that the galaxy is doing. And so we might guess that the same is true for gas temperatures and for the IMF. So our most likely answer should be that even more locally, probably this initial mass function varies and probably has more complicated dynamics. Well, if we're really optimistic, what if we just try to measure this? So what if we take each of these templates, and just for every template, instead of just assuming a Milky Way-like IMF.
What are the different colors here?
So these templates, thank you. Yeah, so these templates are coming from a bunch of different parameters. So this particular color is changing the star formation rate. But this is just one example of about 5 different parameters that go in. So really, this is kind of one projection of like a 5-dimensional grid. And I'm now saying, well, what if we add a 6th dimension? What if we take every one of these?
This is energy flux.
Yeah, so this is the light that you see is a function of wavelength. Yeah. And so what if we just take each of these and we add one parameter? So we get a little family of curves around there. Okay. Now, as you can see, the differences within one of these family of curves are a lot smaller than, say, the difference between a red galaxy and a blue galaxy. So in order to measure this, you need better observations than you did before when you add a parameter. And so what I did is I started working with Cosmos, which has photometry for about 2 million galaxies in roughly 40 different bands. So it's kind of the best of these big photometric surveys we could find. And even for Cosmos, with all of this information, adding a parameter is hard, because in a galaxy survey, most galaxies lie toward low mass. And so that means most galaxies lie near the detection limit of your survey, where you can barely measure 5 parameters, and adding a 6th, you don't have enough information. But for maybe the couple percent brightest objects, we have enough information to add a 6th parameter. But that still means that we've gone from one galaxy where we can measure an initial mass function to tens of thousands. Okay, so what do we get? Well, the surprising thing is we actually get an answer for these gas temperatures that looks a lot like the dust temperatures and a lot like the same kinds of complexity that we saw. Okay, it's not quite 1-to-1 in the sense that in the same location, you have a little bit of an offset between gas and dust. But the behaviors are the same, right? The scaling relations are the same. And the truth is they can't be exactly 1-to-1, because we know that interactions between gas and dust can be a cooling mechanism. And if they were at the same temperature, it wouldn't be a viable cooling mechanism, because there would be no temperature to exchange, right? But the hints are that actually something potentially meaningful is coming out of this, and as optimistic as we had to be to just try to add a parameter and see what happens, it actually looks like we're getting something useful. Okay, so
Inferring stellar mass and separation rate also depends on IMF. So this is just on the basis of one choice of IMF. So
yes.
I'm just saying that there's uncertainty in both the X and Y axis.
Yeah, absolutely, because all of these are measurements that come out of this. So when we change the IMF, we're going to change the stellar mass as well. And so that's the other reason that kind of you should more think about, do the dependencies look like what you would expect, than some kind of absolute calibration. Because to get an absolute calibration, you need some independent verification of one of these parameters, right? But the relative calibration is something that should be robust. And what this is going to do is it's going to change almost all the things that we thought we knew about these galaxies. Because remember, almost all of the mass is the invisible part. So for example, remember those impossibly massive galaxies that we couldn't make under standard cosmology? Well, now we're finding that these earliest galaxies had much higher temperatures than the Milky Way. So we've been significantly overestimating their masses. And the masses come all the way down to something that's consistent with the local relation. So unfortunately, this doesn't mean I get to tell you we've discovered exotic new high energy physics, but it does mean that this is actually a solution to the problem. And it's also telling us that basically this ratio of high mass to low mass stars is important, that it really was important to not use this iceberg approximation and to make sure that we analyze the first galaxies with physics that's plausible for the first galaxies rather than the physics of the Milky Way. Okay. There are a few other surprises that we get coming out of this. Okay, so one example. If you look just deeply at, it doesn't show up so well with this lighting, I guess, but if you look just deeply at sort of any patch of sky, we see it's filled with galaxies. But what I want you to notice is the color. So we see galaxies of different shapes, different sizes, but not completely all different colors. what you basically see is that there are red galaxies and there are blue galaxies, and there's not much else. So the reason for that basically has to do with the stars that make them up, okay? So that when we form stars, we form kind of this main sequence, of stars, ranging from hot, blue, luminous stars, that are less common, all the way down to these more common, cool, red, low mass stars. Okay. But what I want you to notice is how rapidly this luminosity scales. So when we have stars in all of these masses, the light that you see is dominated by these rare high mass blue stars. And so a galaxy looks blue. So a galaxy that's actively forming stars and has these massive blue stars will look blue. Okay. And we have different ideas for the initial mass function, but all of these include blue stars. So whichever initial mass function you pick, these massive blue stars are going to dominate. Okay. Now, if we stop forming stars for a while and let these stars age, in return for being so much more luminous, so a star that's 10 times the mass of the sun might be 3,000 times as luminous. But that also means it's burning fuel at 3,000 times the rate and only has 10 times the amount of fuel to begin with. So the lifetime then is 300 times shorter, which means if a galaxy is no longer forming stars and we let it age, what happens is the high mass stars begin to die. And as it keeps aging and more of the high mass stars die, when all of the blue ones have died, well, now the galaxy looks red. And so the reason we see red and blue galaxies is basically that the blue galaxies are still actively forming stars and the red galaxies have stopped forming stars. They're dead or quiescent, whichever way you want to think about it. Okay. There are a couple observational details here because dust can make a blue galaxy appear red. But here I'm simply talking about what the color of the stars would be in the galaxy. Okay. So from that point of view, red galaxies no longer have their blue stars, so we think of them as dead. Okay. And we can look at the mass distribution of galaxies separately. For the blue star forming galaxies, we can look at the mass distribution at different times, at different redshifts, and we can look at the quiescent ones. And there's a puzzle here, which has been around for a while, and this kind of puzzled me for about a decade, and I never really understood why it should be true. So there are two things that we've learned in general about galaxy evolution that maybe we don't have a good theoretical handle on, but are observationally very clearly established. One is that generally galaxies of the same mass at the same time are doing very similar things. The other is a group of results that we've come to call downsizing that basically says that the most massive galaxies are the furthest along in their evolutionary track at any given time. So if we put these two ideas together and we think about which galaxies are still star forming and which have finished, well, in the local universe, we get what we would expect. So if you think about, say, this red track here, the highest mass galaxies have all finished their star formation, right? This is like 100% quiescent. The lowest mass galaxies, none of them are quiescent. They're still forming stars. It almost looks like a step function, okay? And as you go toward higher redshift, we expect to see the same step function, except it's only, it's only the most massive ones that have finished, right? So it might push to the right. And you see this for a little while, until you get to sort of these blue and purple lines, and then something weird's happened. Suddenly around a redshift of 2, well, now the first ones to quench are not the most massive, it's somewhere in the middle of the mass distribution. And it's not an all or nothing proposition, it's only some of them. So this should have been deeply puzzling, right? Why is it that the process of quenching, the process of turning off, somehow behaves differently in the early universe as at every later time? Okay. But now we have an answer. Because if we think about the initial mass functions that we found, the star-forming blue galaxies are also hot because they're heated by all of these young stars, which means, especially at high redshift, we've been overestimating their mass. Sorry, we've been overestimating their masses. So those masses come down. But the red ones, well, these have already cooled. So we probably have the mass approximately correct. And so when we look at kind of these corrected masses, we go from a lump to the same step function that we expected. And so it turns out that now we basically get the same story at all times. So we still don't understand why it's true that the most massive galaxies are the first to die, but it's at least universally true. So we at least get the same physics at all times again, instead of needing to explain different processes. And maybe the other thing that we can do with this, so if we think about the story of individual stars, maybe the most useful idea we had for learning about individual stars was this Hertzsprung-Russell diagram, where we took kind of something about the luminosity or maybe the rate it's using mass, and we compared it to something about temperature to try to understand how stars work. And we discovered that stars don't randomly live in places on this diagram, but they live in very specific places and tracks that tell us about their history. Well, if we now have an ability to measure gas temperatures in these star-forming regions, what if we try to do the same thing for a galaxy? So here's what that looks like. And like an HR diagram, we find that galaxies don't live all over the map. They live only in very specific locations. And also on what looks like there might be an evolutionary track. So as we go from top right to bottom left, we see that galaxies are getting more massive, the populations get older, it goes from high redshift early times to low redshift later times. Okay. And they cool in temperature, right? So it looks like we want galaxies to evolve from the top right to the bottom left, and these might be different evolutionary stages in the history of the galaxy, right? So some of this we can understand pretty well. The top left, you see from these contours, this is where most of the galaxies are. This is on what we call the star-forming main sequence, where we know that there's some tight feedback that relates the properties of star-forming galaxies to each other. And we know that the ones that were forming stars at the highest rate were the hottest because of that. At the bottom left, this is where the star formation rate's dropping off. So this is galaxy quenching, and of course that explains why it's cooling, right? You no longer have that heating. The puzzle is the top right. Because this says in the earliest stage of galaxy evolution, you have both the most efficient star formation and the highest temperatures. But wait a minute. Star formation is a competition between gravity and thermodynamics. A high temperature should mean gravity wins less often, and the star formation rate goes down. So why is it going up instead? Why is it higher? And we realized, well, maybe we can make a model that does this. So imagine a galaxy initially starting to assemble its ingredients. The baryons are going to have a similar profile to the dark matter before any feedback turns on. They're going to be a very high density in the center and progressively less dense as you go further out. Well, at high temperatures, I need a lot of gravity to win. But I do have high densities in the center that provide all that gravity. So maybe what this is telling us is that this early stage is not really star formation. It's really sort of core formation only. And that therefore these first galaxies should be very compact. Okay. And that's actually something, by the way, that's been seen in some of the first galaxies now with James Webb. But the nice thing about doing this at a little bit lower redshift is you can actually resolve some of these things. So we looked at this with Hubble. These are all galaxies basically at the same redshift of about 0.8. Which means the same radius is sort of the same physical scale. Okay. The top are objects from the top right corner of that diagram. And you see they're tiny, compact, core-forming galaxies. Okay. Then this is the top left, the main sequence. We see the disk is star-forming, is blue. The core has now already become red, right? So they've quenched. And then finally, the bottom left, when they've quenched, the whole galaxy's become red. And so it turns out that this is not just a sequence relating temperature and so forth, not just a galaxy evolution sequence, it's actually a morphological sequence. And it actually gives us a good argument for why the centers of galaxies appear to be older than the parts further out. Okay. So the summary as far as what we get out of the initial mass functions. First off, is there should be some theoretical dependence, but actually we can potentially measure these and get something meaningful. And it fixes problems like this mass that we had before, or like the quenching problem. And it even gives us the possibility of some new kind of story for how galaxies assembled and what that history looks like. So the final thing I want to show you is a different idea that came out of thinking of the same physics, but trying to solve a slightly different set of problems. Because we see that galaxies evolve sort of from blue to red, right? So that when we look at this picture, basically the blue galaxies are star forming and the red ones aren't. And assuming that's true, okay, assuming that star formation really is only happening in these and not these, one of the predictions then is that you should be able to get from a galaxy that looks like this to a galaxy that looks like that without making any more stars. Because if you did, it would be blue again, right? Once it stops being blue, it can't make more stars. So the only processes that you're allowed, you can age, and galaxies can merge together, right? So you can merge stellar populations, but you're not allowed to go make more stars, right? Because the galaxy is not blue, okay? And so we have to explain all of the differences between blue and red galaxies with those two processes. So, for example, blue galaxies have a young stellar population with these massive, and the blue, because these massive stars, red galaxies are missing the massive stars and have an old stellar population. Well, that's exactly what aging does, right? So this one makes a lot of sense. But if we start to look at a couple of the other differences, it's a little bit more difficult. So for example, I mentioned this downsizing, this idea that the most massive galaxies seem to finish their evolution first. So what I'm showing you here at the top, I'm basically showing you the most massive blue star forming galaxies as a function of redshift or time, okay? And what we see is that at high redshift, at early times, you see the most massive. By the time you get over here, the galaxies obviously still exist, but they've all become red. You no longer see them as blue. They finished forming their stars early. At the bottom, I'm showing you the same thing for quasars, for supermassive black holes that grow, because we know that every one of these galaxies also ends up with a supermassive black hole at its center. And there's long been a debate about whether it's sort of a chicken and egg problem, which one comes first, or do they co-evolve in some way, okay? And the fact that they both have the same slope maybe is a good indication that we want some kind of co-evolution idea. Maybe that's a hint in that direction. But let's compare these with what we see. So the most massive star-forming galaxies we see are up to about 10 to the 11.5 solar masses. The most massive quasars that we see are a little bit under 10 to the 10, okay? If we compare that with the local universe, the most massive star-forming galaxies are about a factor of 10 larger. The most massive quasars are about the same, actually, okay? Now, aging is not going, okay, so the quasars are fine, right? Everything matches from blue to red. We do have to grow a factor of 10 in stellar mass, and we're not allowed to do that by making more stars. Aging is not going to solve the problem. That's not making more stars. But merging could, right? Merging just brings stellar populations together, so we could merge and get our last factor of 10, and that would be the remaining mass growth. But there's a little bit of a problem with that picture, because if we imagine, let's say, some kind of coevolution, then what you would expect is that the galaxies that stop forming stars at some time are similar to the ones where they stop growing their black hole at that time, right? Everything looks similar. This is about a 30-to-1 ratio. And you can measure this in the local universe. And in the local universe, there's also a nice relationship between black hole mass. So this is actually just the stellar mass in the bulge, the central region of the galaxy. The full galaxy is a little bit more massive. But there's a nice tight relation here. But the problem is that's not a 30-to-1 ratio. It's about 10 times larger. And that's a problem, right? Aging, we said, can't help us, but merging also doesn't help us. If you merge two things that have a 30-to-1 ratio, the stellar populations come together, but the black holes merge also. So I simply get a bigger thing with a 30-to-1 ratio. If I want to get from 30-to-1 to 300-to-1, I have to grow more stars, but not grow the black hole. So merging doesn't fix this. And there's another problem, which is think about these initial mass functions. We found that all of these are happening above 20 Kelvin. So all these blue star forming galaxies are bottom light compared with the Milky Way. Locally, we actually find bottom heavy initial mass functions. How do you get from bottom light to bottom heavy? Well, again, merging won't do this, right? You have the same population, it's just bigger, okay? Merging won't do this, and aging won't do this either. So if I age this and I lose the massive stars, they look less similar, not more similar. So now we have two problems that we cannot solve. Somehow, what we really need, we need some intermediate stage where the galaxy has to be red instead of blue, or we would select as a blue galaxy. And we have to grow our last factor of 10 of stellar mass. We have to do it with a bottom heavy IMF at very low temperature. And it has to be most of the stars in the history of the galaxy, because this is like 90% of the stellar mass. So what I'm going to leave you with is that maybe there is a mechanism here. So you remember I described star formation and the initial mass function as first you have a big cloud that collapses, and then it fragments into smaller pieces, and that's what determines the IMF. But as we continue to cool, and as galaxies evolve and become more metal-rich and denser and so forth in these clouds, the size of clumps that can successfully collapse gets smaller and smaller. And the Milky Way, it's more like 10 solar masses, but the Milky Way is not fully quenched yet. Let's say you get this down to, say, 2 solar masses. Well, in that case, what you would see is you can't make a 10 solar mass star because the cloud collapses at 2 solar masses. Even if it never fragments, the biggest you get is 2 solar masses. So maybe you could actually get a red star forming phase where we continue to form stars at low temperature, but you can only form the low mass stars that fix this problem because clouds just collapse. They're too cool. They collapse before they reach high masses. So the last thing I'll show you then is we had this idea, and this is a paper that our group just published. But as a follow-up, we then said, well, there's one big flaw with this, because what I've just told you is it's like 90% of the stellar mass that ever gets made in the universe. And every galaxy basically goes through this phase. Why haven't we seen these in galaxy surveys? They better be all over galaxy surveys, right? So we started thinking about what one of these would look like. Okay. Well, they'd have an old stellar population. They'd be dominated by A stars, and they'd have a large low mass population called K stars. Well, it turns out there's a population of things we used to call K plus A galaxies because they have exactly these properties that we now call post-starburst. Because the thought process is that how you make something like this is that you had a rapid burst of stars, it shut off, and all the massive ones died, and you're dominated by the ones that live for 1 billion years, which are these A stars. Okay. But it would look the same as a red star forming galaxy. Could they be hiding in this population? And there's a group at the University of Alabama which went and looked at resolved post-starburst galaxies. So the thinking was that these post-starbursts might all be driven by mergers, that's what makes this unsustainable burst. Okay. They divided them into ones where they could see a merger and ones where they couldn't. And for a merger, what you expect is something where it's structured And the blue core, which is still forming stars, turns off last. The merger stirs up the outer part first and the inner part last. But if it's a red star forming galaxy, as I was showing you, the core has to form first. So it should be inside out, not outside in. And so they tried this. And what they found was the ones that are mergers are basically all outside in, where they can identify a direction. But the ones where they couldn't clearly see a merger, a majority are inside out. So there's a follow-up paper we're about to put out. Actually, there's one version of it on the archive now, and there's a follow-up to that, where we actually show that there are two different, well, really three different populations of post-starburst that could be consistent with this phase. Okay, so that's, I think, a good place to end. The last thing I'm going to say is, if there are any undergraduates in the audience, both the papers I just told you about, and actually every one of the papers that I showed you earlier, had strong undergraduate involvement, including a couple of them led by undergrads. And when I was in Denmark, I was running a summer undergraduate research program that we just started in Columbia this year. It's a bit late to apply for this year, but if you're looking for something for next summer, or if you have any strong undergrads for next summer, we'd love to work with them, and please reach out and we can talk more about it. So thanks.
Thank you very much, Charles, for this nice presentation. Let's start with questions from the students first. Questions? Okay. General question. Okay.
Mentalistic is also changing.
Yes,
Did you take into account the changing mentalistic?
we wanted to. So really what's kind of controlling this, when you do this sort of genes instability calculation between gravity and thermodynamics, it's really a combination of temperature, density, and metallicity. And you'd really like to have a 3-parameter fit. Unfortunately, as I was showing you, going from, fitting galaxies with the typical 5 parameters we've been in the past to one extra parameter cut us from like 2 million to 30,000. Trying to add one more parameter, basically you don't have enough information. So to do that properly, we probably would have to go back to fitting spectra, which is one of the next things we're thinking about. However, there's a bit of good news. If we look both at observations and also some of the simulations, it looks like there's a pretty tight relationship between metallicity as galaxies evolve and these declining temperatures. So there's a decent chance that when we're fitting, that it really does turn out to be a 1-parameter family that looks like this. But this is not something that I can tell you observationally, because we just don't have the quality of observations that would be needed to answer that question. And theoretically, it absolutely should matter, because a more metal-rich cloud is going to cool more efficiently, and that also changes this balance between gravity and thermodynamics.
It should be going the same direction of the effect. If you
It should, yeah. So basically, if you have a higher metallicity clump, it would be the equivalent of lowering the temperature a bit. And so when we actually kind of first wrote these papers, I didn't make a big deal about it in the talk, but the reason that those were labeled as sort of this TIMF rather than gas temperature is because we kind of realized that this IMF temperature that we're getting is really sort of a degenerate combination of temperature, metallicity, and density, which is probably dominated by temperature. And that trying to scale that from that to gas temperature is going to require more observations. But physically, it's exactly what should be happening.
Have you considered, when you have this kind of starburst region that's happening, as some of these higher mass stars die, and you have supernova that occur, they can kind of push outward on gas? Is that included in these calculations, or is that able to be accounted for?
That's a good question. So when we look at the initial mass function, that basically is talking specifically about the clouds that are collapsing, right? So if what happens is that a supernova one thing is it's going to push out and stir up material, and that happens for a relatively small part of the galaxy. What happens for a much larger part of the galaxy is a combination of radiation and particularly cosmic rays, because cosmic rays have a mean lifetime in the Milky Way of something like 20 million years. So they kind of permeate the whole galaxy. The most important effect is that they heat clouds. And this is one of the leading ideas for this feedback, right? I showed you kind of this feedback where it seems like, I mean, this would be a puzzle, right? Normally, if I asked you to predict star formation rates, you'd want a lot of information. But the idea that galaxies are all doing the same thing tells you there's some feedback where it's well regulated. And you saw, for example, that a higher star formation rate, right, was also corresponding to, I'll put up the bigger version, was also corresponding to a higher temperature, right? The leading idea for that, it isn't that the higher star formation rate directly heats things, because a massive star really doesn't permeate the galaxy with its radiation, but rather that the depths of these massive stars and the cosmic ray heating and that kind of feedback is what ends up heating the whole galaxy. So I think this is included in the physics in terms of part of the gas temperature, but observationally, we're really only sensitive to the regions that are successfully forming stars. So we're not really measuring the regions that are being heated actively and unable to, if that kind of makes sense.
Yeah, thank you.
Great. Other questions, please?
I can ask hundreds of questions, but let me just do two.
Okay.
Yeah, so to explain the massive galaxies at high redshift, of course, you talked about IMF, but there are other competitors, right? You know, like too small dust or the starburst.
Yes.
So what is your opinion about other explanation?
So I think these other explanations are also, just because you fix one bit of physics doesn't mean that the rest of the iceberg approximation is correct, right? So there are several other things which we kind of know have to be corrected. So for example, if you think about something like a starburst, one of the things that makes all of this stuff with an IMF so difficult is there's a complete mathematical degeneracy between the initial mass function and the star formation history. That is to say, I can make an exactly identical population of stars today from two different combinations of initial mass function and star formation history. So mathematically, I'm never going to be able to separate the two. And that means if the solution to this is that the ratio of light to mass is different at high redshift, that either could be because you have an incredibly young stellar population, or because you have an incredibly bottom-heavy stellar population, or even both, right? The other big problem that we have is, I even kind of showed you that when you look at resolved images of galaxies, where was it? Sorry about that. Should have had a better way to skip this, but yeah, when you look at these resolved images of galaxies, these are complicated, right? But when we look at these high redshift galaxies, we're not able to resolve them. We have to treat galaxies as monolithic. They have one temperature, they have one star formation rate, they have one star formation history. And we kind of know every time we look locally that that's not true. And that's another kind of approximation. So I think all of these things that we do probably play a role. The physics of the initial mass function, and in particular, the idea that the temperatures are higher than the Milky Way, that seems to kind of be an incontrovertible bit of physics. We know the CMB temperature, we know how that works, we know it's above 20 Kelvin. That doesn't mean these other things are Milky Way-like. You probably would guess that all of them are different. Starbursts probably play a role. You also might guess that the kinds of dust that you get are different at high redshift than locally. So that if we apply dust extinction laws that we've learned from looking at local galaxies, those probably don't work at high redshift. And just as I kind of did this work thinking about the star formation side, you want to do something similar on the dust side and think about the sort of the microphysics there and how that would change. So I don't think it's a reason to assume the rest of the iceberg's correct. I think these all probably play a role. And this is one thing that plays a role.
Another quick one is, the implication to the theory work, where, for example, even in the state of hydro simulation, has to assume subgrid physics, let's say chemical stream flow.
Yeah,
So, let's say you are, explanation is correct, what should we fix?
yeah, so this is something we actually thought about. Actually, one of these summer student projects, so I had an excellent summer student named Riley Tam, and what she did was to work with code that Mark Krumholtz and John Forbes had written called Gidget, which it's a galaxy simulation, but it's a 1D galaxy simulation. So you can get radial dependencies without needing the full 3D complication. And we tried to ask what happens if you tie the IMF to other feedback processes. We discovered a few things. So one is you can get something that looks like these different stages. I can let me see, I might be able to, give me one moment. I can see if I can show it here. But the second thing we discovered is that it's surprisingly hard to put all these things together. I'm trying to find. I'll see if I can. Let me show you this afterward. But we were able to get a simulation to work. But it's surprisingly hard to put all of these things together. Well, actually, because the simulations don't track gas temperature. Or rather, they track some components of the hot gas because that's useful observationally, but they don't actually track the gas temperature in these cool molecular clouds. And so that means if you want to tie, the physics of cool molecular clouds to something about the initial mass function, actually, the first thing you have to do is figure out how to get those temperatures and those conditions, and those weren't tracked. So it should make a difference, and it makes sense that it's part of the feedback model, because if your feedback comes from high mass stars, then it's going to change. The other version of this that I'm aware of is Avishai Deckel's group has been thinking about what he calls feedback-free modes. So basically, ways to take the feedback out of the system. These red star forming galaxies would kind of be an example of the feedback-free mode, right? In this case, it's not that you found a way to remove the feedback from the high mass stars, but simply that you remove the high mass stars, right? Which gets rid of the feedback. But there are simulations with these feedback-free modes that actually start to have some of the properties needed for the red star forming galaxies. So it's a really interesting question, but it turns out that it's probably not as simple of a project as we had hoped, simply because you need to start tracking different kinds of things in the simulations to make that connection.
Okay, is there any other heads and final question? Okay, if this is not the case,